Hello, my name is Tikhonova Maria. I'm a PhD student in High School of Economics and I work in Sberbank as a data scientist.
Hi, my name is Fenogenova Alena and I'm working at Sberbank in NLP research department. Today we're presenting to you our work, Event2mind for Russian, Understanding Emotions in Intents and Texts, Corpus and Model for Evaluation.
NLP has shown significant advances in recent years. One of the spheres where it is developing very fast is a common sense reasoning. Common sense reasoning is considered to be a necessary step towards human understanding. This type of pragmatic inference can potentially be useful for a wide range of NLP applications, especially for those which require accurate anticipations of people's emotional reactions. For example, let us consider a dialogue system. We want it to make judgments about, to react empathically and to make judgments about the person's mental state based on the events the user has experienced, even when the user does not say explicitly how he feels. Among other examples are recommender system, feature extractions from text for ML models, advertisement systems on social media, and so on and so forth. In all these things, common sense reasoning could be applied. The problem of common sense reasoning could be formulated in different ways. In our research, we will deal with the following formulation, which was originally stated in the work Event2mind, Common Sense Inference on Events, Intents and Reactions. The problem could be formulated as follows. Given a short text with an event, which is usually called an event phrase, a model makes reasoning about the agent's intents, reactions, and possible reactions of the other event's participants. Let us consider the following example. Person X cooks Thanksgiving dinner. We want a model to make reasoning about person X's intents, reactions, and the reactions of other participants. Namely, we wanted to answer questions. What are possible intents of person X? Probably to impress his family, for example. What are the emotions? Tired and probably a sense of belonging. How do other participants of the event, for example his family, feel? Most probably impressed, if he cooks well, of course. In the work Event2mind, the authors proposed an architecture, an NLP model for the solution of this problem, and they trained it on the dataset for the English language. The model showed significant impressive results. However, the problem with its adaptation for other languages was that it was data-driven. It requires a huge data set for training, and which is labeled and in a specific format. Thus, to adapt Event2mind model for Russian, for example, we need a lot of data, and which is not that easy to collect. Our main contribution is adaptation of Event2mind for Russian. In our research, we present text corpus for Event2mind training in Russian, a label corpus of event phrases, which is short free-form text about everyday common events in Russian, with the markup. Our corpus consists of two parts: crowdsourced corpus of 6,756 event phrases, and a subset of translated English corpus of 23,409 event phrases. Moreover, in our research, we present baseline models for the Russian language. As was already mentioned, the dataset consists of two parts. Let us discuss the first part, the crowdsourced corpus. the procedure how it was collected could be consisted of 4 steps: data gathering, data preprocessing, data filtering, and crowdsourcing. Let us discuss each of the steps in more detail. Data gathering. First step was to collect a sufficient amount of short free-form text, that is, which we'll further refer to as event phrases or simply events. For this purpose, we gathered text from 3 sources: short episode descriptions of TV series and soap operas. We manually selected 50 TV series from the internet portal Kiss TV. Second source was book summaries from Briefly. In total, we collected 1,512 book summaries. And third source was text from Syntagros Corpus. It should be noted that when we collected events, we tried to select text about common everyday things with general vocabulary. We kept this in mind when we selected TV series, for example. For instance, fantasy series Star Trek is not a very good choice because it contains a lot of vocabulary about spaceships, aliens, star battles, and so on and so forth. And if we want to incorporate our model in the dialogue system, for example, we want it to make reasoning about everyday things, not about spaceships and stars battles. Of course, this is an additional feature. This would be good, but as a main thing, probably not.
Next step is preprocessing of our data. We select event phrases as a combination of a verb predicate with partial arguments from a syntactic tree. Events from raw text are derived using UDPipe syntactic parser. The model was trained on Syntagros. Format of and version of UDPipe text is 2.1.4. Namely, we automatically research for syntactic patterns of verb with its argument in syntactic tree that satisfy one of the following rules, as you can see on a slide. So mostly it's an end subject, some root with action, some verb, and some kind of object. Similar to the original paper, we converted predicate subjects corresponding to pronouns and name entities to the fixed variables of event phrases. For example, as you can see in the picture, Masha пьет кофе в модном кафе. Masha, we converted it as a name entity to the person X. It's our variable. And as you can see from Masha пьет кофе в модном кафе, we took event person X пьет кофе. For the annotation of gathering events, we have done a Yandex.Talk task. First, as you can see on a screenshot, we ask crowdsource workers to check if the event is not a holy bullshit. Next, we ask if it's possible to understand from this event which intents and reactions had persons in these events. And if it's possible, then just write it. We have also introduced some basic variants themselves to our annotators. We have actually an English variant of dataset that we want, so we decided why just don't translate it and make some variants to our annotators. So we translated original corpus, trained model, Event2mind model on it, and the results we pick up and give our annotators as well. Of course, the results of the Event2mind model and translated dataset was bad, but some of them were not so bad, and our annotators check the best of them. As a result, we drop the events that were considered to be wrong by at least 2 annotators, and as overlap of our annotations was 3, we have for about 7,000 events, examples of our data. It should be noted that English corpus is much more bigger than the corpus that we crowdsourced collected. We decided to take some translate English part of the corpus as well. But first, we investigate how the size of the dataset affects the results of Event2mind model. So, as you can see in the table, the data size of the original corpus is about 40,000 examples. But when we decrease the example size to 30,000, you can see that, of course, results gets lower, but not so significantly. And as you can see, 20,000 examples as well, lower, but not so, it's not a disaster. So we decided to take a part of translated English corpus and involve it with, and merge it with our crowdsourced corpus. And as a result, get for about 30,000 examples. The original English dataset was translated via Google Translate. And, well, predictably, the results were poor because there are a lot of short text without context, a lot of English idioms and catchphrases that translated really bad. But the English corpus contains data from different resources. As you can see in the table, here presents data and annotation agreement statistics for all resources in the original corpus, and you can see that the average kappa for rock story is the biggest one, and, well, actually much higher. So we decided to take only examples from rock story training set, as it has the highest annotation agreement statistics, and as it's the best, the translation of it was the best, actually. We also filtered all translated examples ourselves, and some of them actually edited to make it more Russian sound. Now I briefly describe you Event2mind architecture. The Event2mind model aims to generate 3 entity-specific pragmatic inferences: subject's intent, subject's reaction, and other intents participants' reaction. Event2mind is a neural encoder-decoder model, as you can see on a screenshot on the slide. The system is multitask learning, simultaneously minimizing the loss for all 3 decoders at each iteration. Event phrase is given in a free-form short text. First, the input is encoded as a vector. This vector is further used to predict the output, which consists of 3 sequences of words. We have 3 RNN decoders that generate textual short description of any length. The event phrase embedding E is set as the initial state HD of 3 decoders RNNs that can be with GRU or LSTM cells inside. These decoders then output the intent reactions 1 word at a time, using beam search at test time.
To test our model in Russian and to test whether the collected dataset is good and suitable for Event2mind model in Russian, we conducted a series of experiments. In the original articles, the authors performed experiments with different encoders and decoders. And we tried different types of layers in an encoder. We tried LSTM and GRU in encoder and different embeddings models. Namely, we experimented with fast text and word-to-vec embedding from Ruscorpora and Araneum. The results are presented in the table, and for intents, X and O reacts, the metric is recall at K, which is the fraction when the gold falls within the top 10 decoded. That was the metric which was used in the original paper. The higher it is, the better, of course. It should be noted that the metric for X react and O react is quite high. However, it is not that representative because X and O react contain lots of nonce, which contribute positively to the score. However, it doesn't show anything actually. From the experiment, several observations could be made. First of all, it could be noted that word-to-vec embeddings perform a little better than fast text ones. However, the difference is not that significant. Then Ruscorpora fast text embeddings perform better compared with the RNM ones. Then, with word-to-vec embeddings, GRU shows better results than bidirectional LSTM. and intents are quite good and the predictions for them are quite good. Reactions, however, are of poor quality. So, let's look at some example. Let us take the phrase person X ночует у person Y. The model predicts that its possible intents are сильно выпил, влюбленность, негде спать, which could be translated as drunk, in love, no place to sleep. Seems quite reasonable. Then what are person X's reactions? Радость, веселье, быть нужным, удобно. That is joy, sense of belonging and comfortable. Person Y reactions. Радость, веселье, усталый. Joy, tired. Everything seems quite reasonable. Let us take another example. Person X идет в школу. The intents are учить, веселиться, чтобы получить образование. To study, to have fun, to get education. Everything just. And why do we go to school? Just for this. And reactions? Гордый, грустный, довольный. Also quite reasonable. So, in our research, we present a new Russian corpus for Event2mind model. Our corpus supports learning representations over a diverse range of events and reasoning about the likely intents and reactions of previously unseen events. In addition, we trained several Russian models with different configurations with fast text and word-to-vec embeddings, which could be found in our repository in GitHub. The link is on the slide. In the future, we plan to increase the model's performance by experimenting with different language models such as BERT and ELMA, for example. And in addition to that, we have noted that the number of subjects' reactions is quite limited, and it could be regarded as a classification problem. Thus, we plan to train a separate classification model on top of BERT or ELMA embeddings. Thank you!
Thank you, bye!
Bye!